Welcome back to MiniTorch. Today we're going to cover tensor functions and generalize some of what we've learned from scalars to working with tensor objects. Just as a reminder about the notation, we're going to be working with tensors, which are a generalization of matrices. When we have a two-dimensional tensor, it will be the same as a matrix. The first dimension will represent the rows and the second the columns. When working with arbitrary dimensions, we just refer to it as a tensor. This is identical to the array object that you might be used to from NumPy. When working with three-dimensional tensors, the first dimension will be the depth, the second will be the rows, and the third will be the columns. The terminology that we'll use is dimensions when referring to each of the axes. Shape will refer to the number of cells per dimension, and size will be the total number of cells. The size of a tensor is product of the shape. So if the shape is 5 by 3, the size will be 15. We talked a little bit last class about why we can't just use lists. Lists work fine for storing the information we need, but they make it difficult to manipulate the shape, and they also don't correspond to our standard mathematical notation. We'll also see that tensors allow us to implement autodifferentiation and that they allow us to implement things efficiently. Last class, we also talked a bit about the internals of tensors. The data of a tensor is stored in a one-dimensional array. The one-dimensional array has elements that are all the same internal size. For instance, if the tensor is of floats, the storage will just be a 1D array of floats. To get the shape information of a tensor, we have strides that tell us how many positions we need to move in order to move one position in each dimension. For example, here we have a tensor as seen by the user, as well as its underlying storage. The arrows tell us where the data is stored for each underlying position. So we can see that moving from index 0, 1, 2, 3 by 1, so 3 by 1, we have to move 5 positions in the underlying storage. So we say that for this tensor, it has stride 1 by 5, because moving rows only moves 1 position in the storage, whereas moving columns moves 5 positions. We also talked a little bit about how to map both from the underlying storage to the positions in the tensor itself. In today's class, we're going to talk about how to build functions out of the tensors and how to apply mathematical operations to these functions. The core idea is going to be to build an API that allows the user to utilize tensors like their standard mathematical objects. Behind the scenes, we're going to keep track of tensor properties and make sure we can implement things efficiently. Before we talk about tensor functions, I want to motivate why they're necessary in the first place. We could simply apply our scalar functions on each of the values of a tensor. For instance, in this code here, we can add together two tensors simply by adding together each of the individual values. While this would lead to the correct answer, I want to note that the code is relatively messy. Even worse, there's all sorts of other issues that come up behind the scenes. So a couple issues are that this requires writing different functions for tensors with different dimensions. This can be sloppy and lead to errors. Even worse, this leads to a big autodiff graph. For every operation that we apply on scalars, we need to add a new node to our graph. This can make it complicated, and even worse, it will make it slow, because there's lots of Python loops to take care of this graph. Finally, I think this just is a lot of code, and we'll see that the tensor version can be a lot more elegant, if a little harder to follow. So instead, what we're going to do is we're going to wrap the tensor functions themselves. When we do A plus B, behind the scenes, this is going to call forward on a tensor function. This function will manage the whole forward state for that function itself, and also allow us to run autodifferentiation on the tensor. The implementation is going to be very similar to the one we've seen so far. We'll have a function class with a forward and backward static method, It will have the same API that we've seen so far, except instead of working with scalars, it will wrap and unwrap tensor objects. So let's look at some of the operations that we'll see. In general, when we implement these tensor functions, they're going to act like for loops that apply to each of the individual values. This will be relatively easy for us to implement because we've implemented the internal math. But we're going to instead implement high-level functions that makes this math efficient on tensors. To do this, we're going to implement high-level functions that apply to the basic operations we'd like to apply to tensors. We'll then implement versions of these using the higher-order operations we saw in Module 0 when we talked about functional programming. So let's look at examples. So here are 3 tensor functions that we're interested in. The first is a unary style function, such as taking the logarithm of every cell in a tensor. The second is a binary operation. This, for now, will work on 2 tensors that have exactly the same shape. When we call A plus B, we'll get a new tensor that consists of the element-wise sum of all of the elements in A plus all the elements in B. Finally, we'll have reduction-style functions. Reduction will apply to every element, and in this case here, it will return a scalar that consists of the sum of all the elements in tensor A. In all of these functions, things will be immutable. That is, we'll produce a new tensor object that returns the result and will not touch any of the values in the original tensors. As you might have guessed, these 3 operations consist of applying the 3 different higher-order functions that we saw in Module 0. The first will apply a map, which applies to every element of the individual tensor. The second will apply a zip, which takes a mathematical operation and applies it to all pairs. And the third will apply a reduce, which roams over each of the elements in the tensor and returns the reduced value. Let's look at all 3 of these in pictures. First, we have map. Map applies to every element in the original tensor. We can compute a new element simply by applying a mathematical operation to each of these positions, and we end up with a tensor of exactly the same size. Some examples of map include logarithm, exponentiation, and simple operations like negation. Next, we have zip. In the simple case, zip will take 2 tensors of exactly the same shape. It will produce a new tensor of that shape, and every index in the new tensor will correspond to applying a binary operation to the same index in tensor A and tensor B. Some examples of zip include adding tensors together, multiplying tensors together, and applying predicate operations such as less than. Each of these return a tensor of exactly the same shape. Finally, we have reduce. Reduce is a bit more complex. The way it works is that if we have a tensor of shape 3 by 2, applying reduce will give us a tensor back of shape 1 by 2. This is a reduction along the 0th dimension. If we were to instead apply that reduction along the first dimension, it would return us a tensor of shape 3 by 1. It reduces whatever dimension you tell it to shape 1. The way it does that is it adds up all of the elements along that dimension. So in this example here, we're reducing along dimension 0. This corresponds to reducing along the rows. So we sum together these 3 elements and save them in the final 2 remaining elements. So this gives us back a tensor of shape 1 by 2. In general, we will either reduce the full tensor, which consists of summing up all the elements, or just reducing one of the dimensions. So remember, whichever dimension we reduce becomes shape 1. So here's a tensor that's 3, 4, 5. We reduce dimension 1, and that gives us something back of 3, 1, 5. Each one of the final elements consists of summing together 4 of the original elements. That's because we reduced a dimension of shape 4 down to a dimension of shape 1. One thing to be a little bit cautious about is that in MiniTorch, we keep the dimension that we reduced, In Torch and NumPy, the default behavior is to remove the dimension entirely. You can turn that behavior off in Torch, and I generally find it beneficial to do so. As I mentioned earlier, there are two ways that we can apply reduce. If we give no arguments, then it returns a tensor of shape 1. If we give one argument, it reduces the given dimension. So we can apply it in either case, and they shouldn't be too hard to determine the distinction. A couple implementation notes when you're building this yourself. The first thing to note is that all this happens at a higher level than strides. So all three of these operations, map, zip, and reduce, need to work with a tensor with any possible stride. The other implementation tip I'll give is that when implementing these operations, you always want to start with the output tensor. If you know the shape of the output tensor, you should think back about where its values come from. So for instance, in the reduction, if we know the index of the output tensor, it's easy to figure out which values get summed up to produce that final value. Finally, be sure before implementing these functions that you really understand how tensor data works first. You'll really have to become a master of strides in order to implement these higher order functions. Great, so now let's pop back up from implementation land to user land. And let's talk about broadcasting. Broadcasting is one of the notoriously hard parts of PyTorch. I think if you were to ask most PyTorch programmers, only about 5% of them would really understand how broadcasting works. I really want to make sure that you're in the 5%. The main idea behind broadcasting is that we're going to avoid writing loops by making it easier to apply certain operations many different times. We're going to do this by using a certain convention that allows us to save memory in our underlying code. The simple way to think about broadcasting is it's going to apply to zip-based operations. So far, we've assumed that zip could only apply to tensors with the same shape, but we'd like to apply zip in cases where the shapes are not identical. As a motivating example, let's consider adding a vector to a scalar. In math notation, it's perfectly fine to add a vector value to a scalar. This simply adds the scalar to every position in the vector and returns a new vector. However, using our notation so far, we don't have any way to do this. So what we'd like to do instead is to add a vector to a scalar by producing an intermediate vector. We could imagine producing a vector of length 3 and adding it to vector 1. This would correspond to adding the scalar to each position, and we could apply our standard zip operation. However, it would require creating memory for the intermediate term. Another idea is that we could simply write a for loop where we add the scalar 10 to every position of the old vector and store the value in a new vector. This is nice in that it will give us the correct result without requiring more memory, but it has the problems we talked about at the beginning of the class, in that it would be relatively slow in Python and create a complex auto-differentiation graph. Broadcasting is going to get around this problem. The way it works is that it requires no for loops, and it also requires no creation of an intermediate term. It's basically just going to be augmenting zip to allow us to zip together tensors of different shape. Here's another example. Let's say we want to zip together two tensors that are different shapes. Specifically, we want to create a for loop like this, where we have two indices, I and j, and we add together the ith position of A with the jth position of B. This creates a new tensor of alt ij, where we've summed together these two values. It would be very nice to do this without creating any intermediate terms or implementing this for loop. With that motivation, here's what that example looks like in broadcasting. We're going to create an out matrix that's 3 by 2, and we're going to allow ourselves to do this by simply zipping together an in matrix of 1 by 3 and an in matrix of 1 by 2. So in the example, A represents this first matrix, B represents this second matrix, and out represents the matrix to the right. However, note that unlike our original zip example, we're not simply mapping indices to the same index. If we look at each of the output indices, we can see that it's looking at different indices in A and B. However, it's pretty easy to do this map. For instance, if we're in index 1, 1 in out, this corresponds to 1, 0 and 0, 1. Those are really the only indices that make sense for computing that output value. If we know the shape of out, we can figure out where the values come from. But we have to define some rules that will tell us the final shape of out. There are 3 rules for broadcasting in PyTorch, and I recommend memorizing them. The first rule is that dimensions of size 1 broadcast with anything. The second rule is that if we want to create extra dimensions of size 1, we can do that, but we have to do it manually by using an operation like view. Finally, rule 3 tells us that zipping together 2 tensors will automatically create any additional starting dimensions of size 1. If we apply these 3 rules, we can determine whether 2 tensors can broadcast and what the output shape will be. So let's look at some examples. If we have a matrix and a scalar tensor, do they broadcast together? Well, here the matrix is of shape 2 by 2, and the tensor is of shape 1. Rule 3 tells us that we're always allowed to add extra dimensions of shape 1 to the left. That means we can interpret the scalar as being shape 1 by 1. Rule 1 tells us that dimensions of shape 1 broadcast with anything. So that tells us that it's okay, something of shape 1 by 1 broadcasts fine with something of shape 2 by 2. That allows us to add these 2 tensors together. Here's another example. If I have a matrix that's shape 4 by 3 and a vector that's shape 3, can I broadcast them together? Well, it turns out that again, applying rule 3 tells us that we can add an extra dimension of 1 automatically to the vector, which means we can interpret it as being 1 by 3. 1 by 3 broadcasts with 4 by 3 to create a 4 by 3 output matrix. Here are some examples that don't work. If I try to broadcast a matrix that's 4 by 3 by a vector that's shape 4, this doesn't work out. That's because 4 by 3 doesn't broadcast with 4. You can add as many dimensions of shape 1 to the left, but the dimensions will not line up. I can, however, fix this. If I apply rule 2, which says that I'm allowed to explicitly add dimensions of shape 1, I can interpret the vector as being shape 4 by 1. If I do this with a call to view, I now have a matrix that's 4 by 3 and one that's 4 by 1. These therefore broadcast by rule 1, giving us an output matrix that's 4 by 3. It's worth going through some examples to practice this. It's not much more challenging than standard arithmetic, as long as you know the rules. Here are some examples that we can work through. 3 by 4 by 5 tensor broadcasts with one that's 3 by 1 by 5. This produces an output tensor that's 3 by 4 by 5. Similarly, a tensor that's 3 by 4 by 1 will broadcast with one that's 3 by 1 by 5. In this case, both tensors have one dimension that's size 1. These broadcast together to take the size of their joining tensor. The next example uses rule 3. If I have a 3 by 4 by 1 tensor and I broadcast it with one that's 1 by 5, then we can implicitly add an extra dimension of size 1 to the B tensor, making it 1 by 1 by 5. We then apply broadcasting to end up with something that's 3 by 4 by 5. Finally, if we try to broadcast one that's 3 by 4 by 1 with one that's 3 by 5, this will fail. That's because the 4 dimension of tensor A ends up aligned to the 3 dimension of tensor B. These are different shapes, and therefore things fail. One trick I would recommend is to right align these shapes and then go column by column from right to left, checking out if they match up. Finally, here's some more examples that you can try on your own. It's worth just going through a couple of these exercises and getting this cached in your head. Okay, that about wraps it up for today. Next class, we'll go over some more broadcasting examples, and we'll talk about some more advanced cases. The class after that, we'll get to autodifferentiation of tensors, and we'll finish up Module 2. See you then.